Okay, so let's get started. So first of all, good morning to everyone, and thanks for coming to this talk. And today it's our pleasure to have Jim Fan as our speaker. So let me give a brief background of Jim Fan. So Jim is currently a research scientist at NVIDIA, and he's currently building embodied general intelligence, and his research basically spans foundation models, policy learning, like reinforcement learning, robotics, multimodal learning, and large-scale systems. And it's worth mentioning that his latest work, MineDojo, which he will talk about today, has won the Outstanding Paper Award at NeoRIPS 2022. And previously, he got his PhD from Stanford, where he was advised by the prominent scientist Fei-Fei Li. And he has also diverse research experiences at some industries like OpenAI and Google AI. And today his topic is about MineDojo, as I have mentioned. It's one of the outstanding paper in last year NeoRIPS. So now the floor is yours, Jim. You can start whenever you're ready.
Yeah, thank you so much, Kaiyang, for the very kind and generous introduction. So I want to start today's talk with a story of two kittens. Back in 1963, two scientists, Held and Hein, did an ingenious experiment. They put two newborn kittens that have not yet seen the visual world in this device. So as you can see here, it's sort of like a merry-go-round. And the two kittens are linked by a rigid mechanical bar, so their movements are exactly mirrored. And the active kitten on the right-hand side here is able to move freely while transmitting the motion over the mechanical link. And a passive kitten on the left can observe the exact same visual world as the other kitten, but it's confined to a basket and cannot really control its own movement. And then after a couple of days, the scientists test the kitten's behaviors. And they found that only the active kitten developed a healthy visual motor loop, while the passive kitten is not able to do things like navigate visual cliffs or respond properly to approaching objects. So I want to note here that both kittens experience the exact same observation sequence. So the only difference here is agency. And I find this experiment fascinating, right? Because nowadays we have a very powerful passive kitten, and that is called CHATGPT. So it passively observes and rehearses the text on the internet, and it doesn't have any embodied experience. Because of this, ChatGPT's knowledge is abstract and ungrounded, and that's why it hallucinates things that are sometimes incompatible with our physical experience. And I believe the future belongs to active kittens, which here translates to generalist agent. So they are the decision makers in a constant feedback loop, and they not only inherit GPT's vast knowledge, but should also proactively take actions, endlessly explore the world, and learn to make their knowledge executable. And I'm calling this initiative Embodied ChatGPT. And I argue that such an agent should have the following capabilities. So first, it should be able to pursue very complex, semantically rich, and open world objectives, usually specified by language. So you explain what you want in an arbitrary language prompt, and the embodied ChatGPT will perform the actions for you in a dynamic world. And the second property is massively multitask. A generalist agent, as its name implies, must be able to do more than just a few tasks. It should be massively, or even better, infinitely multitask, essentially as capable as human language can express. And third, world knowledge. It should inherit from the passive kitten, having a lot of common sense and pre-trained knowledge, instead of overfitting to only a few concepts in an isolated environment. So where are we right now? Today's agent, despite many shiny achievements, I'd argue they're still not quite there yet. For example, deep reinforcement learning is able to beat human champions on Go, StarCraft, and Dota, but these agents have a singular objective to beat the opponent and can't really do anything else. And then the number of tasks are typically very limited. like a few dozen distinct tasks in many robot learning benchmarks. And reinforcement learning tends to have this tabula rasa mindset. For example, in Atari games, you don't really need any external knowledge to do well. Most of the time, the agent is just trained from scratch, and all it needs is reflex rather than reasoning. So I asked the question, what does it take? And I argued there are three main ingredients in the recipe for a generalist agent to emerge: open-ended environment, internet skill knowledge, and foundation model for agents. Let's look at the first one. The environment needs to be open-ended enough because the agent's capability is upper bounded by the environment complexity. And here we are all familiar. Earth is a perfect example. It's so open-ended that it allows an algorithm called natural evolution to produce all the diverse behaviors of life. So can we have a simulator that's basically a lo-fi Earth that we can still run on our lab computer? And second, we need to provide the agent with massive pre-training data because exploration from scratch in an open-ended environment is simply intractable. And this data will serve at least two purposes. First, it will be a reference manual on how to do things. And second, it will provide guidance for what are the interesting things worth doing. And ChatGPT only learns from pure text on the web. But can we provide the agent with much richer data, such as video walkthroughs, multimedia tutorials, and things like freeform Wikipedia documents? And finally, once we have the environment and the database, we are ready to train foundation models for agents. It should be flexible enough to pursue open-ended tasks without task-specific assumptions, while also scalable enough to convert large-scale multimodal data into actionable insights. And ideally, we want language to play two key roles. The first is an intuitive interface to communicate a task by prompting, and the second is a bridge to ground visual concepts. So these three ingredients land us in Minecraft, the best-selling video game of all time. And for those who are unfamiliar, here's a quick crash course. Minecraft is a procedurally generated 3D voxel world. And in this game, you can do whatever you want. Explore the terrains, mine all kinds of materials, fight monsters, craft hundreds of tools and recipes, or build amazing structures. And Minecraft does require a big set of skills to play well. So what's special about the game is that Minecraft defines no particular score to maximize and no fixed storyline to follow. So that makes it really well suited as a truly open-ended AI playground. And as a result, we see some very impressive creations. Like here in the video, someone built the entire Hogwarts castle, block by block, inside Minecraft. And here's another example. Someone building a really beautiful temple inside a deep cave with underground river. So I want to here highlight a number. Minecraft has 140 million active players. And just to put this number in perspective, it is more than twice the population of UK and 5 times the number of people who know how to code and 10,000 times the size of Europe's. And it so happens that gamers are generally happier than PhDs. So they really like to stream and share. And this huge human mass produces an enormous amount of online knowledge every single day. So here's a question. Can we tap into this treasure trove of learning materials? And just to show one more example of the mind-blowing emergent behavior in Minecraft, here is someone who built a functioning CPU circuit because Minecraft actually supports logic blocks and is Turing complete. And based on Minecraft, we introduced MineDojo, a new open framework to help the community develop generally capable agents. MineDojo implements the recipe I just mentioned, the 3 ingredients towards generalist agent. So the first is an open-ended environment. Next, internet scale knowledge base. And finally, can we learn a foundation model for embodied agents using the simulator and the massive data? So let's zoom in the first one. MineDojo features a massive benchmarking suite of more than 3,000 tasks. And this is among the largest open source agent benchmark ever created, to our knowledge. It is enabled by a versatile simulator that unlocks the full potential of Minecraft. So here, as examples, MineDojo supports multimodal observation space, like RGB, voxel, and GPS, and rich action space, like movement, camera, attack, and inventory management. MineDojo can also be customized at every detail, such as terrains, weather, block placement, and monster spawning. And given this simulator, we introduce around 1,500 programmatic tasks. So these are the tasks that have ground truth, success conditions defined in Python code. And you can also explicitly write down the sparse or dense reward functions. And some examples are harvesting different resources, learn to use a tree of tools, and combat various monsters. All of these tasks come with templated language prompts, like harvest n units of a certain resource in a terrain, or combat a particular monster at night. And next, we also introduce 1,500 creative tasks that are free-form and open-ended. So in contrast to the programmatic tasks that I just mentioned, creative tasks don't have well-defined or easily automated success criteria. For example, let's say we want the agent to build a house, but it's really hard to define what makes a house a house. And this is very similar to the image generation literature. Like you can use simple code to determine whether a cat or a dog has been generated. So these tasks don't really have a simple check, and either human judgment or learned scoring methods, like an embodied FID score, should be used. Finally, there is one task that holds a special status called playthrough, which is to beat the final boss of Minecraft, the Ender Dragon. And while Minecraft doesn't really force you to do this mission, it is still considered a big milestone achievement for any beginner player. And I want to highlight that this playthrough task is an extremely difficult one that requires very complex preparation, exploration, planning, and of course, many martial skills. For an average human, it takes about many hours or even days to solve. And that could easily be over 1 million action steps. So this is probably the longest horizon ever in an AI decision-making benchmark. So here I would admit, I am a below average human. I was never able to beat Ender Dragon myself. So kind of one motivation that drove me to do MineDojo was that I wanted my AI to avenge my poor skills someday. And you may wonder, how did we obtain 3,000 tasks? So we do have a very good task creation pipeline. First, for programmatic tasks, it is simple. We can just do template generation. And for creative tasks, we directly borrow from YouTube and see what are some of the interesting things that the expert human players are doing. And we also find that another way is to just ask GPT-3 for some ideas. Here's the labeling UI that we implemented to curate the tasks from YouTube. So a fun fact, like whenever you see human annotators in our paper, it's just us, the co-authors, dividing up the work. And by the way, we have open source this labeling tool. We built it ourselves, and you can use it to curate more tasks. We also find that GPT-3 actually loves Minecraft. So back then, we didn't have ChatGPT, so we queried the DaVinci 002 API and find that it knows an awful lot about Minecraft. That's not very surprising because Minecraft is the most played game, and it's very likely in the training corpus for GPT-3. So we asked, can you brainstorm some tasks for us? And here are some examples. right? Like design and build a maze out of different stained glass blocks, trap a creeper in a wooden cage so it can explode, make a replica of the Eiffel Tower out of iron blocks. These are very sensible and interesting tasks. And given a task, we find that GPT-3 can also provide step-by-step guidance. So here's an example prompt, how to sail on a boat with a sheep. And you need to append this magic incantation. Let's think step by step. And we can see that GPT-3 is able to generate some instructions. So I want to say it's not always correct, but it's better than nothing. So we decided to just include all of the step-by-step guidance in our MineDojo release, so it could be useful for future research. And here is a sample gallery of the interesting tasks implemented in MineDojo. So moving to the second ingredient, MineDojo features an internet knowledge base of 3 parts: the YouTube, Wiki, and Reddit. And the first is YouTube. We find that Minecraft is among the most streamed games on YouTube, and gamers love to narrate what they're doing. So we collected more than 700,000 videos with 2 billion words in transcript. And these time-aligned transcripts provide a very good signal to ground free-form language in video pixels, so the agent can learn about human strategies and activities without manual labeling. Second, players have compiled a large Minecraft-specific Wikipedia that essentially explains every entity and every mechanism in every version of the game. So we scraped 7,000 wiki pages with interleaving multimodal data. And here are some examples. Like this is a gallery of all the monsters you will ever encounter in Minecraft. And if you click into each of the page, it will explain all the habits of the monsters and the strategies to defeat them. And it also contains all of the crafting recipes, hundreds of them in Minecraft, and very complex diagrams and tables and embedded figures. And finally, the Minecraft subreddit is a very active forum. So players showcase their creations and also ask questions for help. We collected more than 300K Reddit posts. They add up to 6.6 million comments and more than 500K images. And here are some examples of how people are using Reddit as a Stack Overflow for Minecraft. So it's very interesting. Here, for example, on the right-hand side, someone's asking, does anyone know why my wheat farm isn't growing? And we can see that the top voted answers are actually quite good. Someone suggested, you don't have enough light, so you need to add more torches to help your wheat grow. And some other people post on Reddit to showcase their creations. And one use case is that for this portion of the database is that large language models can be fine-tuned on our Reddit corpus to internalize Minecraft-specific concepts and also acquire new strategies. Now, given the massive task suite and internet data, we have the essential components to train foundation models. So in MineDojo, we propose a new algorithm that takes a first step towards the grand goal of a generalist agent. The idea here is very simple. For our YouTube database, we have the time-aligned video clips and transcripts. So here we see, as I raised my axe in front of this pig, there's only one thing you know is gonna happen. This is actually a real transcript that we pulled from one of those Minecraft tutorial videos. And once we have the data, we can train a contrastive video text foundation model called MineClip in the same spirit as OpenAI Clip. So if you're unfamiliar, what OpenAI Clip did was to learn the association between the images and their textual captions from a massive internet dataset. Here, what we do is similar. Intuitively, MineClub learns to associate the video and the transcript that describes the actions in the video. So the score is between 0 and 1. 1 means a perfect match, and 0 means the text is irrelevant to the video. And then we can repurpose MineClub to be a language conditioned learn the reward function for our agent. So here's our agent interacting with the simulator. The task is shear sheep to obtain wool. And as the agent explores, it generates a video snippet, which can be encoded and fed to MineClub. And MineClub will compute an association score. The higher that score is, the more the agent's behavior aligns with the language. And so we know that it's on the right track. And that becomes the reward function to any reinforcement learning algorithm. And in the paper, we just chose PPO as a standard RL technique. So here's a quick visualization of some of our learned agent behavior on various tasks. All right, let's look at some quantitative results. For these 8 tasks, we show the percentage success rate over 200 test episodes. So here in the green circle is 2 variants of our MineClub method. One is attention pooling, and the other is average pooling over the video. And in the orange circle are the baselines. So the first baseline is reinforcement learning training with only sparse reward. And we can see that most of the tasks just fail at a flat line if we only provide a binary success reward at the end, because some of the tasks are quite difficult in exploration. And if you just do sparse reward, the agent will never stumble upon a reward by chance. We also construct a manual dense reward function using privileged simulated state. We implement the reward function individually for each task. So you can think of this column as an oracle result that's close to optimal, because the reinforcement learning algorithm is being shaped smoothly towards the goal. And for PPO trained with our MineClub reward, we can see that we're able to match the quality of the oracle reward in many tasks. So here, it's important to highlight that MineClub is open vocabulary, which means it isn't specifically designed for these benchmarking tasks. And we're simply prompting MineClub with the text description and reuse the same model for all of the tasks. But for manual dense reward, it is unscalable and sometimes even impossible to implement for every new task you encounter. And finally, we also compare against an untrained OpenAI clip checkpoint. It actually performs worse than the sparse baseline, meaning that the OpenAI clip method provides counterproductive reward signal. So this is not super surprising because there is a huge domain shift between the real images that clip was trained on and the Minecraft visuals. We also ask, can our multitask agent that we just saw generalize to unseen tasks, like here, hunting pigs or collecting spider string? So we see that zero shot doesn't quite work because while the MineClip model generalizes as a reward function, the policy itself doesn't. But we do observe that after a little bit of RL fine-tuning, it performs much better. While if you train from scratch using the same sampling computation budget, the performance is much worse. And lastly, can our agent generalize to dramatic changes in the visual appearance? So during training, the agent only sees the default terrain at noon on a sunny day, but we tested zero shot on a diverse range of terrains, weathers, and day-night cycles. And we measured the robustness by the relative drop in performance from the default to the novel test environment. So here we see that a drop is inevitable because there is a big domain shift. But compared to a baseline agent with the OpenAI clip visual encoder, our drop is much smaller. So this is because our agent has a frozen Minecraft visual encoder that has seen hundreds of thousands of gameplay videos on YouTube, which has good coverage of all kinds of scenarios in Minecraft. So this is a testimony that using internet scale data, you will get robustness out of box. So that concludes a whirlwind tour of the MineDojo paper. But I do want to note that MineDojo is not the first testbed for AI in Minecraft. And I want to give a big shout out to many of the concurrent and previous community efforts on using Minecraft for generalist agent benchmarking. So there are at least 3 other testbeds that provided inspiration. So the first is Microsoft Marble. So this project dates back to, I believe, 2016. So this is one of the earliest official release of Minecraft for AI training purposes. So this is official because Microsoft owns the Mojang Studio, which is the creator of Minecraft. And then MineRL is the longest running Minecraft AI challenge at NeurIPS. It laid a foundation for MineDojo, and we also heavily borrowed code from MineRL. So I cannot thank the MineRL team and community enough for making this possible. And there's another challenge called the Eagle Challenge, also at NeurIPS, that uses Minecraft, well, like a clone of Minecraft for grounded language understanding. So it isn't the real Minecraft. It's using like a simpler voxel-based world. But still, I'm very glad to see like many different communities all converging to this environment as a touchstone for AI. Now, looking forward, right? AI has made huge advancements in many other fields, but we're just starting to knock at the door of Minecraft. So one big purpose of MineDojo is to enable new research. Then what are some of the ideas that MineDojo could enable? And I want to share a few with the audience. The first is better reward learning. So in the paper, we have this prototype version of Minecraft, but it has its own limitations. For example, we only trained on 5% of the full YouTube dataset that we provide with MineDojo, and the context length is only like 16 video frames. So that is still pretty short horizon. One obvious follow-up is to scale up Minecraft, both along the axis of longer context length to capture longer horizon tasks, and also along scaling on the dataset. And we want to scale Minecraft on the full YouTube dataset from MineDojo. So actively working on it. And I also want to highlight VPT from OpenAI. So this is a concurrent work. It's called video pre-training. Because both VPT and MineDojo were developed completely independently, actually these two works took drastically different approach towards this problem. And I want to quickly kind of summarize their approach. So what OpenAI did is to also collect, just like us, many hours of YouTube videos in the wild. So they did 70K hours, and that's about a quarter of the size of the MineDojo dataset. And OpenAI also hired many human gameplay experts to play Minecraft and collect all of the observation and the player's keyboard and mouse actions. And once you have this human data set, you can train an inverse dynamics model that takes one frame and the next frame and predict the action that causes the transition between the frames. Once you have this inverse dynamics model, you can use it to label the 70,000 hours of in the wild YouTube videos. So the inverse dynamics model will be noisy for sure. The action labels may not always be accurate, but OpenAI found that it's good enough to augment this imitation learning data set. And then if you train behavior cloning directly on this augmented data set, you can actually get very good long horizon policy. So I would say that MineClub and VPT are very much complementary to each other because MineClub is language condition reward function, while VBT is not a conditional language, but addresses the long horizon policy learning issue. So they have complementary strengths, and it makes a lot of sense to combine them. And next, I want to mention a very recent work called Read and Reap the Rewards, Learning to Play Atari Games with the Help of Instruction Manuals from Yue Wu and the CMU group. So in this work, they did not do Minecraft, but I believe this approach is applicable to the MineDojo Wiki dataset. So the rough idea is the system receives the current frame in the environment and also an instruction manual on how to play the game as input. And then a QA extraction module extracts and summarizes the relevant information from the manual. And another reasoning module will assign auxiliary reward to detected in-game events. So that provides a higher quality reward signal. And I think this is not limited to Atari and can very well be applied to MineDojo. So next idea is world models. Minecraft probably has one of the most complex world models of agent learning benchmark out there. So can we learn this world model and use it to train actors in a latent imagination space? Another very recent work from DeepMind called Dreamer v3 is able to train on in Minecraft and obtain diamond from scratch. So this is quite an achievement, and I'm very impressed by the result. And another work that came out very recently. So can you do planning with ChatGPT while combining with low-level control policies? So you have like a full system to play Minecraft from language. So here the idea is, again, quite conceptually simple. You have ChatGPT that receives the current state of the game as a string, and then it produces a plan. And if the plan executes and fails, then ChatGPT will receive that feedback as the next portion of its dialogue, and it will continue to plan until the task is successful. So this is another interesting work. And the last idea, if you just want an excuse to play Minecraft at your lab or in class, I believe MineDojo is also perfect for you. When you get caught, just tell your boss, right? You are collecting human demos in MineDojo for training embodied ChatGPT, and that's for science, right? So we have open source everything. This is our website, minedojo.org. It features a gallery of all of our data sets and some cool animations. Please check it out. We open source the simulator, the benchmark code, all of the pre-trained Minecraft models and checkpoints, YouTube annotation tools, and a lot more on our GitHub. And it's linked in the website. And last, I want to close with a reminder to all of us that despite all of these very cool follow-up works, what we can do so far is still very much away from the ingenuity that human players have demonstrated, such as decorating a winter wonderland or simulating the CPU circuit, as we saw earlier. So here's a call to action for the community and to all of us. If humans can do these mind-blowing tasks, then why not our AI? So let's find out together. And this project is a big teamwork at NVIDIA. I'm super grateful for all of our team members and advisors for making this possible. And if you're interested, I post a lot of announcements on Twitter. Welcome you to follow, and please reach out to me over email if you have any follow-up questions. And if you want to try out MineDojo, you get first-class support from us. Thank you so much.